Hello everyone and welcome on this conference. So I will be speaking about how to design a microservices architecture to exploit the benefits of serverless. But first, let me introduce myself. So I'm Laurent Grangeau. I'm a cloud solution architect at Sogeti, and I'm also the organizer of the Paris Serverless Architecture Meetup, and I'm an MVP Azure. You can follow me on Twitter with the nick handle @LaurentGrangeau. And I give different talks about Kubernetes, serverless, and all over the containers world. So, why do we need microservices in the first place? So, microservices, from my point of view, is to be able to scale horizontally an application. If you don't need to scale horizontally an application, you don't need microservices. Of course, you will have some benefits over microservices. You will have products and not projects, so your team will be working on projects. You will have decentralized governance, and every team will be able to govern how the product will be driven and how will be the future of the product. You will also have decentralized data management. So it will be, for example, you will have lots of data sources, data stores with MongoDB, SQL Server, big data, something like that. And of course, microservices are independently deployable. Okay, so first of all, how we can break a monolithic application in microservices. So the first part is to separate data with multiple data stores. For example, you will have not a big SQL server, not a big database, but multiple data stores who will handle data from lots of microservices and who will be scalable horizontally. And you will do it step by step. So you will extract microservices from the monolithic application one at a time. So you will not be doing like big bang refactoring of your application, but you will need to wrap your application, your monolithic application, in an API server, for example, and you will start extracting services from your monolithic application to microservices. And then you will create business logics with services in mind, and you will have like lots of independent microservices, and you will be able to scale it horizontally. The best way to do that is to use DDD, domain-driven design. So why using DDD? So DDD enables you to have different bounded context. So you will have, for example, a sales context and a support context who will be evolving independently of each other, and you will have like a shared model who will act as the bridge between the different contexts. The context will be isolated, will be loosely designed, and of course reusable. You will also have separated layers of your context, and you will create some microservices based on that. And the last one, and the last benefits of having a domain-driven design approach, is to have minimum dependencies between microservices. Because if you have strongly coupled services between each other, it will not be able to scale horizontally, and you will not be able to deploy it on virtual machines, for example. So, what is microservices in the Kubernetes world? So, of course, microservices in the Kubernetes world will be in containers. So, you will have some images containing all of your application, all of the version of your application and microservices. And it may be like a polyglot application. For example, you can deploy Python images with a Node.js images and a Docker images with a Java, Spring Boot, what you want. And these containers will act with each other with some kind of bridges with DNS, for example, or a service mesh like Istio, if you have deployed one in Kubernetes. In a Kubernetes world, you will have one container containing one microservices. You will not have a container containing all of your application, but one container containing only your services. It will enable you to deploy this container in multiple nodes with Kubernetes, for example, or multiple Kubernetes cluster. This design, with the help of Kubernetes, of course, is scalable by design. And of course, it's fault tolerant because you will have not only one container, but multiple containers with multiple microservices. And that's enabled to have resilient applications based on containers, Docker images, for example, or containerd or OCI images. Okay, so now we know how to split your monolithic application in containers, in microservices, but here we are talking about serverless. But why, in the first place, do we need to have serverless? Serverless is not a new product. It's not what you want to deploy as part of an application, but it's an architecture design. Based on this architecture design, it's event-based. If you have no events for your containers, it's not serverless. And of course, serverless is highly scalable. Lots of benefits of the serverless. It's scaled to 0. For example, you only pay what you consume. If you don't have any requests on your containers, you will have no containers at all on your Kubernetes cluster, and you will not pay for this compute. Of course, you will have to pay for the Kubernetes cluster, but if you have, for example, an IT infrastructure who will enable a Kubernetes multi-cluster for you, you will not have to pay for the whole cluster. You have, of course, millisecond response. If we are talking about containers, between the start of the containers, the event received in the containers and the response, you will have like tens or hundreds of milliseconds. And depending on your application, it may be, of course, lots of seconds. But the main advantage to have serverless is to have a millisecond response. One other benefit of having a serverless application is to not worry about your infrastructure. So in a serverless world, you will not worry for your infrastructure, and you will not having servers to provision or manage. If you want, a Kubernetes cluster will auto-upgrade itself, or you will have a one-click button to upgrade your cluster. And with a serverless world, and of course Kubernetes and containers world, you will have built-in disaster recovery and high availability by default, because Kubernetes cluster enables you to have highly scalable, resilient application based on containers and who will replicate themselves across the cluster. And of course, with serverless, you will have infinite scalability because you will treat your cluster as one big cluster, and you will treat all of your events as multiple containers starting based on that event. So this is why you will want to use serverless. So in the Kubernetes world, we are in the Kubernetes Breakathon from Scaleway. You will have lots of framework. OpenFast is one of the most common framework, but you will also have Kubeless, Fission, and kNative, for example. kNative is a project from Google that you can deploy on top of whatever cluster you want. We will have some demos, like 5 demos with kNative. to demonstrate how to deploy serverless application. And we will use, of course, Kapsule from Scaleway to deploy that part. Okay, so for those who don't know already kNative, so kNative is basically a framework serverless based on Kubernetes and containers, and contains two main parts. The first one is kNative eventing that will generate or create events based on what you want to do. You have also kNative serving to route and to consume these events. You have, like, for example, a subscriber, broker, channel, trigger, and we will see that later on. And the third part is, of course, STO. That is a server mesh to connect all of these microservices to be able to interact with themselves. We will not deep dive into STO because it will be a whole other story, but we will use kNative as part of our demo to demonstrate the power of serverless and kNative. Okay, so as I said, we have now microservices. We know how to handle microservices, how to create microservices based on your monolithic application, and we aren't yet serverless. We aren't yet a serverless application. As I said, a serverless application is based on events. So the first things to do is to create events. Fortunately, kNative supports events, and we can define some events based on that. And we have some common events like API server source, which is Kubernetes events. We have also Apache Kafka, which can generate events, and your application will be based mainly on that. We have also container source, GitHub, GitLab events, and so on and so forth. We have also even more events based on the community, and if you want to see the repo, the GitHub repo of kNative, we have all sorts of events. The second part of eventing in kNative is based on cloud events. So what is cloud events? Cloud events is a tentative to have like industrialization of lots of events, and normally we have a normalization of events based on cloud events. It's a specification for describing event data in a common way. It integrates with kNative eventing, of course, Falco, which is security runtime on top of Kubernetes, OpenFaaS, Tekton pipelines, etc. Like in cloud events, we have lots and lots and lots of events we can treat and you can consume. Cloud events enables you to have consistency across your deployment, like portability, because if every event is self-described and it's not interoperable, it's not possible to deploy events across Kubernetes cluster. And of course, cloud events enables you to have accessibility, because you will have the same seamless experience between a Kubernetes cluster, which will be a Kapsule Scaleway cluster, or even other clusters. Okay, so now we know how to create events to be able to have bridge between your microservices, and there is 3 different ways to deliver your events across your kNative application. The first one is a simple delivery. So you will have events created and consumed by Kubernetes service. The second one is a complex delivery with channel and sync. You will see that later. And the third one will be broker and triggering. And we have, of course, we can have, of course, complex deployments of all of that with flows like sequence and parallel, but we will see that later. Okay, so the first one is a simple delivery source and service. Okay, so we have an event source that that will generate events, and we will consume that event with a service, with a Kubernetes service on top of that. So we have a first demo here, how to consume a single event within the Kubernetes service, and let me show you that. So, because I'm on stage and I can't have my laptop, I will play a little video which will demonstrate how we can create an event and consume it with services. Okay, so I will comment on that. So the first thing to do is to create a service. So this is a service based on event display, which will just redisplay the event. The second one is to have a source. The source will be a ping source, which is native with kNative, which will send hello Breakathon, and which will send this event at event display. So let's first create our service, then create our source, so our ping source, and let's deploy it in the cluster. And then we can see the log of the service. And if you are seeing the logs, you will see that we are receiving an hello Breakathon based on the cloud events. So this is a cloud event generated by kNative. So this is the first one, the first delivery method we can have with kNative, that is a direct delivery from one source to a service. But you know that it's not this simple to create an application, and you will have to have channel brokering, complex workflows, stuff like that. So let me dive into that just after that. So the next thing to have is to have a channel. Channel will receive events generated by our source and will consume events. So you will see that we have lots of channels. You have GCP PubSub, for example. kNative is sponsored by Google, so it's normal to have GCP. You have in-memory channel, which will not be used in production, but you will use in-place Kafka channel. You have consolidated and distributed channel. And of course, we have NATS S channel, which is NATS streaming channel. In this slide, you will see how we can define a channel. So here we are defining an in-memory channel, and we will see how you can consume or subscribe to the channel. So the first one is to describe a channel. The second part is to define a sink. A sink is another resource on top of Kubernetes, that acts as a link between an entity system and an entity event image, and an entity or system. We can define like a Kafka sink and a Redis sink. I apologize because the image is not about sink but about trigger. But you can define a sink like you see the two last line. You will define a Kafka sink, for example, and all of the event will be sent to the sink. Okay, so now we want to have a more complex architecture. So in this architecture, you will create a channel with subscriber, and subscriber will send events on services. So this is a very simple architecture with channel and subscriber. And you will see that you can subscribe to any events and even filter these events to receive, for each service to receive an event. But you know, in a real world, it's not this simple. And you will also have to define this more complex architecture. So this is the same channel with same subscriber, but the service 2 is responding a new event based on what he received. And the service 2 is generating a new event and send it to a new channel to be received to the service 3. Okay, so here is a little demo, a second demo based on channel and trigger to see how it's working. Okay, here we are defining in-memory channel. So this is for the sake of the demo because you don't use that in production. Here we have the subscription. So you have the channel subscribed with a subscription, and you have the subscriber, so the service which received the event. In the third place, we are defining a new service. It's an event displayed, which displays the events received. That's the same as one at the first demo. And we have our ping source, which generates a new message, like a Breakathon from Scaleway. And you will see that this ping source will send the message to the in-memory channel. So the first step is to create the channel, of course. The second step is to create the subscriber from the channel. Then we describe the service, and then we create the ping source. And you will see that the ping source will generate a new message. And let's see how the channel is being received. Okay, so it's a little bit quick, but the service have received a new event, sorry, based on that channel, and all of that is being sent through the channel. So this is the second demo I had, and how to demonstrate the power of channel and trigger. Of course, like I say, in a real-world application, having like channel with subscribers is really complex to maintain. And if you want to have like a new service subscribed to a new channel, or if you have like, for example, hundreds of channels and hundreds of subscribers, it's very difficult to maintain. So the next thing is to create a broker. Like a Kafka broker, like you will use in the real world. And a broker is used to publish event. It's like a channel, but it's more easy to maintain if you have multiple subscribers. You have 4 different brokers. You have the in-memory channel, you have the Kafka broker, you have the empty channel-based broker, and of course GCP. And this broker under the hood use channels to, of course, for event routing. And if you have a broker, you will need a trigger. A trigger is what? Is a desire to subscribe to events from a specific broker. Like here, you have a trigger, which is subscribed to a broker, like a default one, like the 5 or 6 line, and send the event received to a service. And of course, we can do filtering in the trigger, and we can filter the event before sending it to a service. But we'll see that in the demo later. Okay, so now our second architecture is simpler because we have a broker like an ESB if you're old enough, and all of the trigger connected to the broker. And all of the trigger will be connected also to a service to send events received from the broker. So the last architecture I saw you is simpler, so it's simpler to understand. I also have a demo to demonstrate the power of broker and trigger. And let me show you that. Okay, in this third demo, we have defined a broker. So this is a default broker. Here, because we are going to consume Kubernetes events, we are going to need a new service account, which will listen to events based on the Kubernetes, and we will define this service account inside the API server source. So here we are defining an API server source, which will generate events based on Kubernetes events, and we will use service accounts based on that. We will also define a resource to create like a kind of event based on Kubernetes, and we are going to define also the broker which will receive these events. The next step is to define, of course, the trigger. And the trigger will listen to events on the broker. So this is the default broker. And will send these events on the service, on the Kubernetes service. And of course, we are defining also a new service that is the same as the previous one, which is only to display events received by the broker. Okay, so let's deploy that on top of my Kubernetes cluster. So we will use kubectl create with the definition. So the first broker is already defined. That's why you have this kind of error. We are creating a new service sequence to be able to listen to Kubernetes events. Then we will define like the broker and the events generated. We will also need to create the trigger based on the broker to be able to trigger, of course, the service based on the events received. And we are creating the service which will just display the events created. Okay, so now let me just see if the pods are running. So you see that one of two pods are ready. So let me just wait for a second. Okay, so now the pods are running inside the cluster. Let me just create a new containers and then just stop it to create an event like some Kubernetes events to see if it's working. So if we are going to see in the events generated, you will see that the pods isn't created because if you see the reason, you have a failed scheduling, and we can regenerate a new pod, a new event. So let me just create a new event. So I do the same as before, and you will see that, and the reason is now scheduled because we have received a scheduled events from the Kubernetes side. So that's how we can define a broker, which which act as at the bus, for example, generate events based on Kubernetes, and then listen to these events. And you can imagine, for example, having a new service that reacts to these events to, for example, define some security, some alerting, some monitoring based on that. Okay, so now we have like broker and trigger. So that's how you can define events and consume them in a Kubernetes world, in a serverless world. The last part I want to show you is to use parallel. So what is parallel? Parallel is like you want to have multiple services work as one. So you will define a parallel. So this is a parallel with event filter, event transformer, hot filter, hot transformer. I will explain that to you later. And it's a list of branches that act as a parallel. You can think of that as a fan out of your serverless or functions. So you see, you have your first functions, and then you fan out, so you multiple your workers, your functions, based on events. So I also have a demo for parallel. So in this demo, we will create 3 services, which will generate odd and even number. So the first one will create even number. So it's in the definition of the service. And we also have the odd number. Okay. But we also need to transform this event or odd number to be able to send messages based on the number received. So we are even for the even number, and this is odd for the odd number. So this is like a transformation service. Okay, so now we are creating our display. So it's a service to display the events created and received. And then we are defining our parallel sequence with different steps. Okay, so we have a channel, an in-memory channel to receive events, and we are defining 2 filters that act as steps. The first one is event filter with the subscriber as event transformer, which will transform a number received with a message. And the other one is odd filter odd transformer, which will transform the number received. This is odd as a message. And of course, we are sending this reply as to a sink. We have our ping source, which will run every 1 minute. That will generate numbers every 1 minute, and we are sending this number to the parallel. And you will see that the event received by the parallel will be spread across 2 different steps. So the first step is to create the filter transformer inside our Kubernetes cluster. And then we will define a service, so the event display service. Then we will define a parallel, so this is all of the function running in parallel. And of course, we are creating our ping source to be able to generate events based on that. So now, if we are looking at event received, we can see that we are receiving a number that we are even, a number that is even. And every 1 minute, a new number will be generated, and based on if we are even or odd, we have a message, we are even if the number is even, and this is odd if the number is odd. Okay, so now this is how you can do parallel tasks, parallel functions in a Kubernetes world. And the last one I wanted to show you is sequence. Sequence is a way to define an in-order list of functions that will be invoked. So for example, if you want to chain function based on a sequence, like the definition, you will use a sequence. In this example, we have 3 different services, one named first, the second named second, and the third named third, obviously. And each of these service will be chained from one to another. The overall architecture I will be deploying in the last demo will be the ping source, which will generate events, subscribe to a broker. The broker will send events to the sequence, S0, S1, S2, and then just resend the message to the broker, and the event display will display the message received. Okay, so let's see the last demo I have. So in the 5th demo, if everything goes well, okay, we are defining the first service, which will create a message handled by 0, so the S0. The second service will be handled by 1, S1, and the third service will be handled by 2, S2. The S2 will also define a new type, which is mod3, which will send back to the broker. Then we are defining a new sequence, the channel, in-memory channel, and then the sequence of the 3 different services. The first one is first, second, and third. And if we have a reply, the reply will be sent to the broker. We are also defining the ping source, which will be triggered every 1 minute, and we will send hello breakathon from sequence. And of course, we will send these events to a broker. And the last one, of course, if we have a broker, we will need a trigger. So we are defining a trigger. We will filter only events received by the ping source. And of course, we are defining the sink, which will be the display message. Okay, so this is the sequence display. Okay, so let's create all of that. So we are creating the steps. You remember steps 1, 2, 3, first, second, third. The sequence. So we are defining the kNative sequence to be able to act, to chain our functions. We are creating the source, of course, the trigger, and the last one is to create the display. And okay, so we will see all of the events sent to the sequence. So there is a little bug in the ping source or the appender. So you will see lots of images, lots of messages. Sorry, lots of events. But if we are going to deep dive into this message, so this is the bug. But if we are going to see the message sent, you will see that the sequence have been appended, handled by 0, handled by 1, and handled by 2. So you see that we can create sequences very easily based on YAML file. And as a conclusion, I wanted to show you like we have a rise of a serverless application patterns, like we had in ESB world with enterprise integration patterns. You will see that we can have a dead letter sync. So if an event, a message is sent but not received by a service, you can have a dead letter queue which will store the event, and then you can replay that after. And of course, there is a circuit breaker supported by Istio that acts as long as the message is sent, about 3, 5, 10 times. If you want to stop the sending of the message, it will secret break and stop the event. So you can see that we are creating a new serverless application patterns that we will use inside our application. So in this session, we have seen how we can break down architecture from monolithic application into microservices for horizontal scaling. There is lots of benefits to have, of course, microservices, but this is the most important one for me. We have seen that serverless enables complex workflows with sequences, parallels, broker, triggers, stuff like that. We have seen that, of course, because we are talking at Scaleway Breakathon about Kapsule, you can use containers to achieve serverless architecture. And I think, in my opinion, that in the near future, like in 2, 3, 5 years, we'll see that not only you will have containers running aside of serverless containers, and we will have a melting pot of containers and serverless containers running all together. And of course, thanks to frameworks like kNative, Istio, it's easier to define cloud-native applications with service meshes. I'm talking about Istio, but there is a lot of service meshes inside the community. And of course, Kubernetes enables us to have resiliency, scalability, fault-tolerant, disaster recovery as part of our cluster. Okay, so thank you, everyone. You can follow me on Twitter with the handle @LaurentGrangeau. Thank you, Scaleway, to have me on stage to talk about how we can create like serverless applications. And we'll be back after a few breaks.